And I'm especially glad to give a talk in a conference in which you are also remembering Professor Rajashekaran. So he was my teacher. I was an undergraduate student at CMI, and he taught us along with Professor H.S. Mani. He was, and many other faculty members at IMSC at that time. They were leading the physics program at that time, and he taught us 2 courses. I remember one on quantum mechanics, and then one in the final year on special and general relativity. And not only the courses, he encouraged us in many different ways and helped us in many ways. And I especially remember, so Professor Murthy's talk title, it had this inward bound, and he insisted that we should read the book Inward Bound by Abraham Paes to learn about the history of quantum field theory and particle physics. So I'm very glad. And although I'm not an expert in neutrino physics, in fact this is when this paper comes out, this will be my first paper on neutrino physics. But I decided to talk about this because, as Professor Murthy mentioned, towards the later half of his career, Professor Rajashekaran was very much involved in this INO project, which was a magnetized iron calorimeter experiment. And the large collider detectors that I am going to talk about are also of the same type, but of course much smaller in size. And today I will not talk about astrophysical neutrinos as such, as the title said, but only about atmospheric neutrinos. So this talk is based on this paper, which is probably going to come out this week. And I must mention that most of the hard work has been put on by Deep Ghosh, who just finished his PhD last year with me at ISCS, and now is a postdoc at ISER Kolkata. So since the audience is broad, let me first review a little bit about atmospheric neutrinos. So atmospheric neutrinos are produced in the interaction of primary cosmic rays, which are mostly protons and a little bit of other heavier nuclei, with the air molecules in the atmosphere, which is mostly nitrogen and oxygen. And depending on the energy of the primary proton, the different mesons can be produced in these interactions, like pi mesons, k mesons, and so on, which subsequently then decay to generate a flux of atmospheric muons and neutrinos of different flavors. Now, at low energies, the most copiously produced mesons are charged and neutral pions, where the charged pions and neutral also, they decay before reaching the sea level. So if you consider a 10 GeV pion, it travels only about half a kilometer before decaying. And a positively charged pion will decay to give a muon and a muon neutrino, while a negatively charged pion will give a muon anti-neutrino. Now, muons also decay, but with a much longer lifetime. If their energy is less than around 2.5 GeV, they will decay before reaching the sea level. So the atmosphere is around 15 kilometers high, and for muons with energy larger than this value, they don't decay before reaching the sea level, and therefore their decays do not contribute to the neutrino flux for those energies. Now, if you put these things together, then you see that at lower energies, when the muons decay before reaching the sea level, for both the positively charged pion and the negatively charged pion decay chain, you produce a muon neutrino and a muon antineutrino in equal amounts. So the ratio of muon neutrino to muon antineutrino is order 1 up to a GeV or so. If you go to higher energies, as we just discussed, the muons do not decay before reaching the sea level, and therefore this ratio starts to increase, because positively charged pions are produced more often than negatively charged pions, and this has to do with the valence versus sea quark PDFs. At even higher neutrino energies, the k mesons start to become important, and they are produced in large numbers, and with more k plus than k minus, And if you look at these decay branching ratios of K meson, you see that most of the time you will produce a muon neutrino. Therefore, putting all these facts together, this ratio of muon neutrinos to muon antineutrinos, if you average over all zenith angles, will be around 1.2 at 10 GeV of neutrino energy, and will grow slowly with energy. So, it will be around 1.4 at an energy of 100 GeV or so when kaons become important, and even higher at higher energies. These numbers are obtained by using certain flux models, the famous Honda flux model, and I will discuss how different flux models differ later on, well, in this slide itself. So, these are the different fluxes and flux ratios. So, if you look at this first figure on the top left, it shows the muon neutrino and muon antineutrino fluxes averaged over all directions, and with energy you can see that the difference between them is increasing, which is further shown in this ratio plot down here. And the important thing to note here is that if you compare the muon neutrino to muon antineutrino flux ratio predicted by different models, then they differ quite a lot at higher energies. So, at energies about 100 GeV or so, they differ quite a lot. At lower energies, the differences are smaller. These of course come from lack of knowledge about fragmentation functions and so on that are involved in these models. So, given these significant uncertainties in the muon neutrino flux ratios, it will be interesting and probably important if we can measure this in experiments. So, that is the goal of this talk. Now, a brief remark about atmospheric neutrino detection. So, although neutrinos are the most abundant cosmic rays at the sea level, detecting them is very difficult because of the small neutrino nucleon cross section. So, if you average over neutrinos and antineutrinos, the charge current cross section is around 10 to minus 38 centimeter square times the energy of the neutrinos in a broad energy range. And the flux of neutrinos around the GeV, if you sum over all directions, is around 1 per centimeter square per second. Okay. So, if you put these two things together, then the interaction rate for a 1 GeV neutrino, which is the important quantity for the detectors. So, this is the flux 1 neutrino per centimeter square per second, and this is the interaction cross section per nucleon. So, given this small value of the interaction cross section, you need a large number of nucleons to have some events, and if you put together a kiloton of material, that is around 10 to the 32, 6 times 10 to the 32 nucleons, but that is also not sufficient. You need to wait for a long time. If you wait for a year, you expect around 100 neutrino interactions per kiloton year for a 1 GeV neutrino. Of course, the flux of the atmospheric neutrinos fall very fast with energy. So, at higher energies you have much smaller numbers. So, the takeaway from this classic estimate is that to study these charge current interactions of neutrinos that we are proposing to study, we need a detector at least a few kilotons in fiducial mass, and it should run for at least a few hundred light days. And in addition, to distinguish neutrinos for antineutrinos, which we wish to do using these charge current processes, we need a detector that can distinguish between charged leptons and charged antileptons, and then possibly with a magnetic field. Now, both these conditions are met by a detector that operated earlier, which is the MINOS experiment. Although MINOS was operated primarily using a neutrino beam, it carried out a study of atmospheric neutrinos as well when the beam was off. It had two detectors, a near one, smaller one, and a far detector which is much larger. The far detector had a weight of around 5.4 kilotons, but around only 4 kilotons fiducial mass was available for atmospheric neutrino studies. It had a magnetic field of around 1.3 Tesla in the far detector, so they could distinguish between neutrinos and antineutrinos. And they made measurements of the atmospheric neutrinos for about 2553 light days, and had a significant statistics around 2000 candidate events of different types, which I will discuss later. And based on these events, whether the events were of content vertex type or whether they were induced by the rock below the detector, they obtained this ratio of muon neutrino to antineutrino, or rather charge muon to minus charge muon to plus charge muon, to about 2.2 or 1.6 with different statistical errors. However, the energy dependence of the ratio that I emphasized earlier was not reported by the Minos collaboration. Now, what we are proposing to do is to use the Atlas detector at the LHC for the same purpose. So, Atlas is the largest collider detector that has been ever built. It has a length of around 44 meters and a width of around 25 meters and weighs 7,000 tons. There are two magnet systems, 2 Tesla magnet for the inner detector and 0.5 Tesla in the barrel region, and in the end caps around 1 Tesla for the muon system and calorimetry. And the important thing to note, given this estimate that we had of the mass required to detect atmospheric neutrinos, is the fact that the Atlas hadron calorimeter, which is mostly iron, has a weight of 4,000 tons, 4 kilotons. This is a cross-sectional view of the Atlas detector. This central line is where the beam comes from, and it it collides at the middle point. And on both sides there are tracker elements of a meter, a little more than a meter in height, followed by electromagnetic calorimeter of a similar size, and then a hadron calorimeter of height around 2 meters, followed by a muon chamber which is around 7 meters on both sides. So, the muon chamber defines the shape or the span of the detector, and they are rather large. So, the first requirement is met by Atlas. It has a large fiducial mass. How about the second requirement of the time required? Now, the LHC beams are not in circulation during the winter months, while the detector and the magnetic fields are on during most of this period. They are on for different reasons, for example, for cosmic ray studies and for detector alignment and other checks. So, if around 100 days per year are available with the detector and V fields on, but the LHC beams off, then in 10 years you can have 1,000 live days for doing such neutrino physics. If instead only 60 days per year are available, you will need a longer period, around 15 years, to have the same statistics. Now, given the very long timeline of the LHC and the HL-LHC, these 10 years and 15 years periods are certainly feasible. So, what kind of events do we expect to see at Atlas induced by atmospheric neutrinos? There are, for content vertex type events, there are two distinct possibilities. One is that, so let us consider downward going neutrinos. So, these downward going neutrino might interact either in the upper part of the hadron calorimeter or in the lower part of the hadron calorimeter. If it interacts in the upper part of the hadron calorimeter, then it will pass through the tracker, the produced muons in DIS will pass through the tracker elements and then go to the muon chamber. If on the other hand this neutrino interacts with the HCal material on the lower half, then it will not have any tracker elements and it will directly go to the muon chamber. Same thing for neutrinos going upward, so passing through the earth, and there are two types of events, one for which both the tracker and the muon chamber information are available, and a second category for which only muon chamber information is available. So, for low energy muons, we definitely need the tracker information because they do not go much far in the muon chamber to learn about their momenta and the charge by bending in the magnetic field. So, for low energy muons, we can only use events where both the tracker and muon chamber information is available, whereas for high energy muons, only the muon chamber information is sufficient. The length of the muon chamber is sufficiently large, so that from the bending in the magnetic field, we can know both the momenta and the charge of the produced muons. Now how about backgrounds? So the ATLAS detector is not sitting at a very large depth, it's around 100 meters only from the ground. So cosmic ray muons are a large background. However, the distinct event topology helps in reducing the background. Consider, for example, a cosmic muon entering from the, so cosmic muons always enter from the top and go down, okay. So they are always down going. So this is how a cosmic muon trajectory will look like. However, for the signal, the neutrino travels a long distance, 7 meters, into the detector and then converts into a muon in the H-gal. Therefore, these downgoing cosmic ray muons cannot mimic downgoing content vertex atmospheric neutrino signals, right. So these cosmic muons will necessarily hit the muon chamber first and then go down, but these muons will not hit this upper part of the muon chamber, it will only hit the tracker elements and the muon chamber downstairs. What can be problematic is the second type of events, where these neutrinos travel to the upper part of the hadron calorimeter and then become a muon. That might be mimicked by a cosmic muon which does not have a large energy and which stops at the hadron calorimeter, right. In that case, these tracks look similar. However, the LHC has very good timing ability. In particular, the muon chamber has these RPC plates which have a timing resolution of 1.5 nanoseconds. And to travel this 7 meter distance in the one part of the muon chamber, a muon takes about 23 nanoseconds. So we can decipher whether the muons are hitting the upper muon chamber plates first or the lower muon chamber plates first, and by using this timing information we can also veto this kind of cosmic ray muon events. So all in all, the conclusion is, by either using the special topology of the neutrino events or by using the timing information, excellent timing information that is available with these detectors, we can eliminate cosmic ray muons even though the detector is not sitting at a very large depth. So now what about the event rates? So to know the event rates, let me briefly recall the neutrino-nucleon cross sections, and here the main point to note is that neutrinos have larger cross sections than antineutrinos with nucleons, right. So there are different types of processes possible: quasi-elastic, resonant inelastic, and finally deep inelastic. It is deep inelastic which dominates from a few GeV or so for neutrinos and from around 10 GeV or so for antineutrinos, but in all cases the neutrino cross sections are larger than the antineutrino cross sections. So it is a deep inelastic that we shall focus because we will be dealing with mostly higher energy neutrinos, and so this is a approximate expression for the neutrino-nucleon deep inelastic scattering producing a mu minus and anti-neutrino-nucleon deep inelastic scattering producing a mu plus. And the quark contribution for the neutrino scattering is not helicity suppressed. So this is the quark contribution, whereas the anti-quark contribution is helicity suppressed, and conversely for the anti-neutrino case, and that leads to this difference in the cross sections that I mentioned. Now when the muon energy becomes close to the neutrino energy, then this helicity suppression is lifted and the cross sections become of the same order. But as the energies are different from the neutrino energies, so this y goes towards 1, the cross sections differ widely. So these two facts together will decide these muon numbers that we observe in the detector. So there is a twofold enhancement of the muon to anti-muon number, right. First, the flux of muon neutrino to anti-muon neutrino, and then this cross section factor which is larger for muon neutrinos compared to anti-muon neutrinos. So putting them together, these are these content vertex events that ATLAS may be able to observe if you have this 1000 live days exposure that I mentioned, which is 11 kiloton year exposure, and this is the distribution of the events for these kind of events as a function of energy. For energies larger than 3 GeV, so we start at 3 GeV because we cannot do muon physics at LHC below 3 GeV. A muon with energy less than 3 GeV does not reach the muon chamber and so cannot be identified as a muon. So we start from 3 GeV onwards, and these are the muon numbers and anti-muon numbers expected for all the events higher than 3 GeV. So, these statistics is not so bad, and if you take the statistics, the ratio that we discussed in the beginning comes out to be around 1.9 or so. However, these events are without this selection criteria that I mentioned. We must impose the selection criteria that the muons should go through the tracker elements and the muon chamber if they are of lower energy, and if they are higher energy, then both kinds of events can be accepted. So, and of course, they have to be in the rapidity range of 2.5 or so. So, if you impose those selection criteria, then between 3 to 10 GeV you have around 31 mu minus and 17 mu plus. So, the statistics comes down and we will be dominated by statistical errors. The ratio comes up to be around 1.8. As you go to higher energies, the ratio increases, as we discussed it should. However, the statistics become poorer and poorer for these content vertex type events. So, to improve the statistics, we have to take help from these external upward going events that I mentioned for MINOs. So, this is the ATLAS detector, of course, it is not to scale, and this is the Earth. And for the neutrinos going from down, they can interact anywhere in the rock column and produce a muon, which will then travel to the detector. Now, the range of the muon, the distance that the muon travels depends on its energy. So, higher the muon energy, higher distance it travels, and therefore, the volume of the rock column is larger and larger. So, taking into account these kind of events will increase definitely the statistics. However, the events are less striking compared to these content vertex events that I mentioned. Now, if you compare the signal and the background, so the signal here is the neutrino converts to a muon somewhere down here, and then the muon travels to the detector, and this is the cosmic muon. So, the only information that you have to distinguish between these signal and the background events is the timing information. So, for cosmic ray muons, they will first hit the upper muon chamber and then the lower muon chamber, whereas for the signal it will first hit the lower muon chamber and then the upper muon chamber. So, for these events, as I said, the statistics is much larger. These are the distributions as a function of energy for mu minus and mu plus, and as you can see above a 3 GeV or so, you have around 700 mu minus and 341 mu plus events, which is pretty large, and the ratio is around 2. So, as I mentioned, the higher energy neutrinos contribute to these kind of events. Therefore, the ratio of mu minus to mu plus expected is also larger for the reasons that I explained earlier. The flux also grows as a function of energy. And as you can see, even if we go to higher and higher energies, we still have sufficient statistics with this upward going events, and we can study the energy distribution of this charge ratio using these external upward going events at the ATLAS successfully. So, this is just a final summary plot which shows the mu minus to mu plus ratio as a function of energy, which, as I said, MINOS did not report, but ATLAS has the capability to measure, and this is for the content vertex muons. We can only go up to energy of 20 GeV or so, because the event rates fall so fast and it grows with energy in the way expected, whereas for these external events we can go easily up to 100 GeV or so, after which the statistics is not good enough to get the ratios correctly. So, that is the summary of the study. So, to summarize the whole thing, the ratio of atmospheric muon neutrinos and anti-neutrinos, as I tried to emphasize, is an important quantity, and there is still a large uncertainty in its prediction in the flux models, especially at higher energies, and therefore, it is important to be able to measure this ratio directly in experiments, in neutrino physics experiments, as a function of the neutrino energy. However, most neutrino detectors do not distinguish between muon neutrinos and anti-neutrinos, simply because they do not have a magnetic field, which magnetized detectors can do in an event by event basis. So, detectors like Super Kamiokande with gadolinium and so on put in can statistically figure out anti-neutrinos up to energies of 10 or 20 GeVs, but not in an event by event basis. So magnetized detectors can of course do that, and MINOS has done that up to a good level. So the point of this talk was that we already have large collider detectors like the Atlas at the CERN LHC, which have the fiducial mass required, so around 4 kilotons for the Atlas Hadron Calorimeter, and they are extremely finely instrumented. Because they are small and collider detectors, they are much more finely instrumented than large neutrino detectors, and because of this fine instrumentation, even if they are not at a very great depth, they can reject cosmic muon backgrounds. So we have a finely instrumented large enough detector to do some neutrino physics, so we should do it. And in more detail, what I showed is, while content vortex events are very striking, they do not have enough statistics at high energies, but these upward going events, which are produced in the rock column below, have a much larger statistics and can determine the energy distribution. So I end here, and thank you.
So thanks, Satya. There are too many questions. Okay, maybe we can start from first row. So
okay, so yeah, that's a nice work. But how do you determine the charges of the muons?
There is a magnetic field. So from the bending. So
from muon chamber bending or from the tracker?
Both. I mean, depends on what it passes.
But if it is from the tracker, then probably we will not be able to do it because the tracker volume is small.
Yeah, I showed that. So it has to reach the muon chamber to be called the muon, and then you have a large arm length. And then from the bending, like measuring the sagitta of that, you can know the charge. So it's a standard muon charge determination. So it has to reach the muon.
Nice talk, Shruto. If you go back to the previous slide, so I'm curious, so there are two sources of this ratio not being 1. The first is, as you said, that there are, there's an overabundance of, let's say, muons over anti-muons or whatever, and the other is the cross-section is different. Now there are errors that will come from statistics, there are uncertainties that will come from the statistics, and uncertainties that will come from the lack of knowledge of the cross-sections themselves. So yeah, the systematics. So once you fold that in, at what, let's say, statistical accuracy can you establish that you've discovered the original asymmetry between muons and anti-muons?
Right. So the dominant uncertainty is actually in the flux, not in the cross sections. So the cross section uncertainty is of the order of 5% or so at higher energies, and whereas the flux uncertainty can go from 15 to 20%. So which is what we are trying to pin down by doing.
So you can put it the other way around, no?
Yeah.
You've put in the model, right, which has a flux ratio of something,
right,
and you're getting out a flux ratio of something. So how different are the two? That's really, I think, his question, or also my question.
Well, I mean, I thought he is asking how much the cross-section uncertainties also matter, and so right. So of course you can compute using different flux models and then make an estimate of the uncertainty in the prediction from the flux model.
Is this model you have put in 2 and you're getting out 2, is it? You put in some flux?
No. So the flux model goes only, the model that we have put in only gives you around 1.5 in the flux ratio, the higher energies.
Whatever you put it, you should get out, right?
No.
That's what his...
But then there is a cross section also on top of that.
Be able to extract it?
Yeah, so the question is, can you deconvolve that part?
So we are not doing the, so you see what I am plotting here is R mu minus by mu plus only, right? I have not gone back and plotted R nu mu by nu mu bar. For that I have to do the unfolding. So that unfolding has not been done. So given a flux model, given a cross section, this is the prediction. You change the flux model, you take into account the uncertainty in the cross sections, there will be a band, right? So what that band is, I do not know, but as I said, the cross sections have an uncertainty of around 5% or so at higher energies, and the flux models have an uncertainty of 20% or so, right? And so the question is whether the measurement can reduce the flux model uncertainties by being a new input, right? So for example, the muon, charge muon to minus charge muon to plus charge muon ratio, right, at sea level, that's an input to these flux models. What we are trying to propose is this can be an additional input to the flux models.
Yeah, I have a different question. So this is an interesting idea, but have you talked to people on Atlas at all about the triggering of these events? Because I think the contained vertex would be a new trigger,
Right.
and the external upward going events should already be there in their existing cosmic data, I think.
Right. So that's a very interesting point. And I did talk to several experimentalists, all of them in CMS, because in India we mostly have CMS people. In particular, I talked to Professor Sunanda Banerjee, who is one of the leading experimentalists in CMS. He said the triggering is certainly possible, so it will be done with a single muon trigger. And as you said, data already exists with single muon trigger. But somebody has to go and look into that data and see whether you have such events. And he also told me that doing the analysis with beam off, but the detectors on and the magnetic fields on, for around 2-3 months a year should also be possible.
Hi, thanks for the nice talk. I have a sort of a nice question. So one input that you need to calculate is the atmospheric neutral flux at these latitudes, at these geomagnetic levels, and that varies. It also has a function of the zenith angle, and I think that is not there for the CERN site.
Correct.
So that will bring an additional uncertainty that has never been done at the CERN site. So that has to be redone if you want to do this thing.
I agree. So, I mean, I just use the standard ones, and the fluxes that I used are for the Kamiokande site.
Okay, but that's
No,
it can't teach.
So it's 100 meters. And and the zenith angle dependence also was not studied here so far.
Yeah.
So I used an average flux over all zenith angles. But the site may matter, and we don't have a flux per CERN site. So.
Okay, thanks.